No. So yes, a little bit nervous to present. So yeah, today I want to present you the subject like collaborative space planning. Like I will give a little bit introduction about me. I'm currently a software engineer in microseed industries. That my previous work was software and research engineer on Arrival. And this talk is based on my experience from the Arrival. So I want to tell you a lot about microseed industries now. You can speak about it after the talk. And yeah, the project on which this talk is based is autonomous, like factories fueled by autonomous robots. And actually, yeah, so the collaborative space planning is the thing that you need to deploy if you have if you plan to use a lot of robots for the things in the environments like warehouses, like video games, miniature labs. If you know, this thing, they don't use collaborative space planning; they use people to do it. But yeah, it also can be solved by the things. Also, like the traffic routing, and yeah, so you need to employ it. Yeah, the first problem you actually face when you're trying to solve this problem is, as many things in the industry, like academia, we have so many names for one thing. So, yeah, just and then it's a few, but it's even more. So it's the first problem you need to solve when it's when you want to do it. But yeah, it's easily solved already if you make a simple assumption that the agent is the robot. So I will use these terms interchangeably during this talk. Okay, the definition. Yeah, that is quite simple. That you have a set of the agents, and you have graph. It can be undirected or directed. It's it's not important. And you have starting points for your robots and the target points. And yeah, what you need to get from this algorithm is the set of passes. And so any robots won't collide, and they will all reach their destinations. And the curious listener may ask me, why? Sorry. Yeah, and the curious listener can ask me why I speak about graph here and not, for example, about rods, because rods something doesn't look like an active graph. But the thing that's here is we can actually discretize any space and make a graph for almost everything. Yeah, it will, if you want it to be precise, it will cost us in time and complexity, but for all the cases we can use it. Okay. Let's now talk about the algorithms. The first set of the algorithms I want to present you, I call it search-based. And let us remind some basic to the beginning. In the beginning, there was Dijkstra. It's pretty old algorithm, searching for the shortest path in the graph. And it's cool, but it has one drawback. It searches in any directions when it's trying to find the shortest position. And again, it's not cooperative, so if you want to have many robots, it won't work. Then people invented A*, and A* is just an extension to the Dijkstra to give it some understanding where to look for the next node. And yeah, they use some heuristic to just choose another node to direct a search. Still not cooperative, and the problem, how to use better heuristic, because they're different and can give you different results. And the first algorithm that's actually cooperative called local repair ASTER. And the idea is super simple. You just use A*, and whenever robot faces another robot, you just replan. That's the idea. It's super simple. It doesn't work for many cases because, again, you don't take into account that this can be bottleneck or cycle. You just replan. And this algorithm actually was used in many video games back then. So it's pretty old also. And what we can do to actually take into account like not only like the space dimension, we can introduce the time dimension. And like the cooperative S-star algorithm introduced this time dimension by the term reservation table. So you can simplify this. Imagine we have a 2D map, and we just extend it in the time. And then we start to search for target position, not only like in the one point in this table, but any nodes in the time dimension is now okay. But what we will do is just like when we plan, we will book the next step for the agent. And there is like still some problems that for the cooperative A-star, people use heuristic Manhattan distance. Performs pretty well, but still not as good. And it's like depending on the order of the edges. I will show you on the next slide where it is important, like why it is important. But the next thing like is hierarchical cooperative A-star. The hierarchy, by the way, I will share all the slides, so it's on my GitHub, so you can already access it. Hierarchy in this sense means just like different steps of the algorithm. Instead of like doing the search in three-dimensional space like all the time, we just use 2 dimensions as a heuristic. So we plan for the robot the heuristic how to choose the next node in the certain 3 dimension based on the best in the 2 dimensions. So we remove all the robots, plan for the shortest path, and use this information to search in 3 dimensions. And for the hierarchical cooperative A-star, this is very nice like optimization use. It's reversible, resumable A-star. And the idea is simple. So you plan not from the starting node to the target, but from the target to starting. And it helps you when you deviate from your path, you don't recalculate like everything, because probably you need to slightly move to deviate slightly from your path, and then like A-star gives you shortest path. And this is the example where the order of the edges is important. So if, for example, if I have in S minus one agent and S plus 2 another agent, they're probably already in a bottleneck, because if you will just plan the shortest path, they can block each other. But I just realized it's not the right picture. But it's like the idea is simple. The one robot can block the road for another. And the hierarchical cooperative A-star has the 2 problems already. The agents fixed their load conditions, and the second problem was the first one. They're sensitive to the agent order, and we need to calculate the route in the big 3-dimensional space, and what we can do to solve those problems. And here is a window hierarchical cooperative A-star. The idea is again quite simple. We now search not in the whole space, but only in some window, in a 3-dimensional window on the time reservation table. And the idea is that in the beginning, we search in the 2-dimensional space, just a shorter path, and then we check this path only by the window in the 3 dimensions. And if the agent see in this 3-dimensional reservation table another agent, it starts to take it into account. All the other time you're going to the best, because, for example, if you will try to imagine, if the robot doesn't have any conditions, for example, they're moving in a totally distant passes, the path you calculate in 2 dimensions is the best path. Another cool features of the window hierarchical cooperative A-star is your target position is not anymore a goal. A goal is how you reach this target position. So it's set of the actions you need to do, and this helps to solve the problem of of the robots stopping on their target positions. Because then if you will push another robot to go on the blocked path, this robot won't stay anymore like on another robot won't stay anymore on the occupied position. It will replan because for it, it doesn't like needed to stay on the position. It's need like to only like have a pass at this position. Yeah, and the experiment environment for this surge-based algorithm was this map with quite many robots, like S is starting positions for the robot, and G is goals, top goals. And yeah, on this environment, is like you can see the result and the performance of the algorithms. So as you can see, for example, window hierarchical comparative A star, like in the brackets you see the size of the window, like this D steps, and it's performed quite well. So for like 100 robots, almost like the percentage of the success is almost like 100%. And the cool thing is you can implement this algorithm if you choose to write data structures. It works pretty well, and it's even like can be suitable for the real time. So you can actually employ it like and recalculate it many times as you need it. Yeah, this is number of cycles, to the number of edges. So for the window hierarchical cooperative cluster, there is not so many cycles. You have even like this 100 robots on this environment. And yeah, and now I will tell you about like a different approach to the same problem. And I call this approach network flow based because it's actually based on the network flow. Is also like a pretty old concept. Like you have a graph, and the important for this algorithm is that you have these two functions. One define capacities and one define costs for the edges. And again, you have the set of the sources and you have the set of the targets. In the terms of the network flow, it's sinks and sources. And then you define those two constraints. One is the edge capacity constraint, and it's basically telling you that like every edge has the capacity, and you cannot push more like flow through the stage that this capacity has. And another constraint is the flow conservation constraint. If you push some flow through the node of the graph, the same amount of flow should go out of this node. And yeah, that is actually it's all definition of the network flow. And like to give you some more understanding of it, it's like a flow, like imagine two things connected by the pipes, different pipes, and then you push water through the pipes. So the network flow algorithm give you the optimal like path in this sense. So you will push so much, for example, water through those pipes, so you can push like you can push more. Yeah. Then yeah, that's actually told you what this algorithm is doing. So it's either the maximum number of humans can be transferred from the source nodes to the sink nodes. And this is like the optimization function where we basically optimize a number of flow and visual extra cost. But you can ask me now, like, what we can do with it to solve our cooperative bus planning problem. We can again like incorporate the time space, and the idea is that you can construct your graph in the way so the nodes won't be connected anymore directly, but they will be connected by taking into account the time to go from one node to another. So, for example, on this picture, you can see that from the S plus to the X, it takes 2 seconds, for example. And on this time expanded graph, you can see that for S plus to the X, it also takes 2 seconds. And Yeah, so you basically you choose some time point, some limit, and you expand your graph like by taking into account the time. And but it's not the only requirement. You also need to incorporate some other things to manage robots going from the cross section, so they don't have a head-on collision. And yeah, you can implement what's called in literature gadget. And like that is a little bit sophisticated. Probably showed on the next slide how it's constructed. But the idea is, yeah, this gadget is solving the problem of the head-on collision. So you can see that from the node u in the time t, the robot can go to the node v in the next time step, and the same for the vice versa. And yeah, it's to solve the head-on collision. And also you need to introduce some holdover edges. It's again to avoid some collisions. But the cool thing, if you do it in this way, yeah, if I can show this slide for longer so you can read it. Yeah, I can. Yeah. The constructing of that's a little complicated, but yeah, not that much. So you can just take a paper and implement it. And the cool thing, if you implement it this way, for the single commodity problem, it will give you the optimal values. And it's wonderful because for the many algorithms, you don't have optimal values. And in this case, if you have the solution, it will be optimal. You cannot plan in any other space. All the other algorithms will give you worse solutions. And to explain what is the single commodity, like the idea, there are two types of commodities, single and multiple. And the single means that there is no straight connection between the robot and the target. So any robot can go to any target. You can think of it like a taxi drivers. Like when you call a taxi, probably mobile application on the server for the taxi app can use the same algorithm, so it just give you the closest taxi driver. Yeah. But there are few problems in this implementation portfolio. The problem felt that you need to find the optimal T, the time expand, like what is the time expansion you will use. And yeah, that's the problem. And yeah, so I actually implemented this algorithm, and I just used bisect to just use the optimal one, like just going and bisecting the time space. Yeah, and it's not for the real time you can see, because it's again on the time expanded graph, so the graph is huge. And yeah, in the mentioned thing, it's not for the multi-commodity problem, but we probably want to use something for the multi-commodity. And there is a solution for the multi-commodity problem. The beauty of the network flow approach in overall, it's in its it's mathematical, because it's actually just a few inequations and equations. You can then use inter-linear programming solvers. So you can just code it in your solver model and ask algorithm to solve it. Yeah, I didn't mention it here, but the problem of the multi-commodity problem, if you want to have an optimal value, it's you cannot attain it in a feasible time, so it's not polynomial problem. So you cannot, in any cases, find the solution that will be optimal and on the in the polynomial time. Yeah, you know what it's like. Yeah. But yeah, we can incorporate the solver and some optimizations with slight loss of the optimality. And how to do the code? I mean, if somebody is not familiar with the solvers, yeah, the code is super simple. You basically literally code in math in the Python, for example. Yeah, here I use the Google's how the name of the library? Solver. or tools. Yeah, I use or tools here. Yeah, and again, for the optimizations, I will just quickly go through it. For the time expanded graph, you can imagine that, like we expanded, I show you that we expanded for all the nodes, but we actually don't need it because robots are staying only on the sum of the nodes. And you can, for example, and on the next time step, a robot can go only to the nodes it's connected. So you can incorporate some algorithm to remove all not required nodes. Yeah, battery collision encoding constraint. I showed to you the gadget. It's here, and that is complicated. It solves its problem, but yeah, we can probably use something a little bit simpler. Yeah, this is how we can employ head-on collision. And the next thing, what we can also do is divide and conquer approach in the time domain. What it means. So what we do, we can basically first plan in the 2D space, again, pretty familiar with what we did in the story-based approach. And we can then split the shortest paths in the 2 dimensions on the equal parts of the space. And then we can just try to solve, like in the time domain, the same problem. So it won't be optimal because we are trying to do like the best path. But yeah, the cool thing is all these models work pretty nicely if the number of the variables in your model is small. So yeah, it's actually like reduce the complexity drastically. And for these, like this was the experimented environment for the experiment. And this result, the majority of the cases were solved within 10 seconds. And solution, you can read it. And the result, actually pretty impressive. So, from this slide, again, it's an optimal solution, or nearly optimal solution. It's just like, it's my visualization of the implementation of the algorithm. The pinks agents, red rows, and green targets. Yeah, and actually, like it works. So if you will implement it, it will solve the problem. But yeah, it takes a huge amount of time without the optimizations. And even if you introduce these optimizations, it's still like not for real time. The conclusions about the search-based. No fancy linear solvers, and it's actually like pretty cool. So if you implement it, you're pretty sure how your algorithm behaves, and the implementation is much simpler. Like it's quite simple. No guarantees that it's optimal, but yeah, it should work for most of the cases, and kind of ready for the real time. It's a program implementation. For the network flow, for example, the single commodity, which is can be physically solved, and it can work for some tasks. If you can imagine the cluster, like mobile robot cluster formations, you can already use it because you are not interested in each robot. You will go to form a cluster. You can just take any robots to meet their decisions. Guarantees of the optimalities, but doesn't scale. I mean, you don't know how much it will take to solver to find out the solution. This is the papers I used for this talk and for this project. I will share the presentation on my GitHub. Yeah, I'll also write it there if you want to make it. Okay. And yeah, thank you for listening. We still have 5 minutes for the questions if there are any.
Yeah, so you legal this research, but your experience with survive?
Not for the whole character, but yes, because we had, like I did that we had many new robots, and we need to operate them in a factory. So it was a part of the research to solve this problem.
Have you implemented it?
Yeah.
I really go right all these now able to scale.
We didn't implement it on the real robots, so only on my experiment environment. But yeah. There's just so many. Like, let's just begin in this work, please.
Here you have a search-based route, so kind of two-dimensional colors. You have higher dimensional. I guess you're referring to this. You have high dimensional these methods.
This for the question being, again, this is not for this kind of problems. For example, in a higher dimension, you will use random RT, how I don't know. Yeah, or some sample-based algorithms. So it's not like those algorithms are not for like high-dimensional space. As I showed you, it's only for the three-dimensional space. So for the 2D map, and it's mostly like for the wheeled robots actually, because wheeled robots are living in the two-dimensional space, and you can add like only the times there.
Technical, then I have a small question. If the algorithm was in a cohort, and I think that's just a scenario that people accidentally cross. So suddenly there's a new map, and how is it work with the search algorithm? So is able to deal with this reaction?
Yeah, sorry, I just realized I didn't take the microphone for all this time.
Yeah, but actually, it's really good.
Yes, thank you for the question. The idea of algorithms is I think they cannot work only on its own. So you need to implement many stuff, and some of the stuff should run on robots. And you probably should connect all the robots like through some network, so it can communicate with the server, and you probably do planning on this server. So you still have some local planners on the robot, but yeah, it's kind of for the global planning, not for the local planning. And yeah, then you need to decide what you do in this case. So it again depends on the task. So what you need to do, you need to start the robot, or you need the robot to replan. It depends. For example, if you are on a warehouse, you probably, in a fully automated warehouse, you probably don't expect people to suddenly appear. Yeah. And what you should do there, yeah, it's not the part of the algorithm to decide what you should do. It can give you a new path how you can overcome the obstacle. Yeah. This is really fantastic.
I think you mentioned two types of problems. One is each robot has its own very specific goal, and the second problem is that you set up start goals, and it doesn't matter which robot goes to which robot. Two problems, the network problem. Do you work like with network and flow problem? The solution. Are there also people those problems, or is it the graph search just for the one-to-one correspondence and flow just for the
with a linear solver, you can use it to one-to-one. But yeah, if you don't want to incorporate solvers, linear solvers, it's just one-to-many. Yeah, but the search base is one-to-one. If I understand you correctly, so you're asking, is there like search-based algorithms can work for the multi-commodity problem where you have robots attached with target codes, and the network flow only for robot doesn't attach to this codes? Yeah, no, with the binary solver, it solved the problem of this like connection between the starting pose and the target. But yeah, then it doesn't scale. This.
So I'm interested in dynamic environments. So when you say that the flow-based solution is not interesting, the kind of field version. So I'm mentioning this warehouse solution. Probably you have to compare the search base, then we will have provision for the value. And now it's interesting, okay, how do we compare that with local compare? How did that do with any experiments? See how it compares, like the graph shows, it's like how much better you get the search based method compared to local compare.
You mean like on this slide, yes, comparison?
But there's no local compare.
There is local repair.
The
first one is the local repair as start.
Yeah.
And you can see that it doesn't scale well with the numbers of robots. Because again, like the problem, if you don't like take into account the time dimension, you're basically blind when you need to move many hundred robots. So you're trying to plan, but you don't know where is the next robot will appear. Because if you're starting to take into account, you won't solve this problem. So the algorithm is impossible to implement.
I'm sure you guys are not going to compare that. I see that there's targets. I guess there's no rules. So we have some kind of like smaller rules like a target system or something like that.
I think definitely it's possible, but first it's out of the. I think it won't be any more the local repair answer. It will be probably some other algorithm, and I think there are pretty few of them. I didn't like. I mean, the algorithms I showed you. It's not like the only algorithm. There are pretty many other algorithms to solve the same task. And again, if you want to incorporate some extra logic to this algorithm. Yeah, it's why not? And probably somebody
basically the question is more things of that is already or not collaborative, right? So it is like a system I always say more complicated if I have to make the decide together where to go. So it is like doing something substantial.
Look, I think for example the cool thing about local repair start it's highly parallel, like you can run in parallel. I mean because you plan basically for any agent. And it still will work, and it will work pretty fast because you can run everything on the engine. The question is how then you will deal with the bottlenecks. For example, like we did some experiments, and the problem with increasing number of the robots is that you either run quickly in the bottlenecks. So in one moment, some robot just blocked the road for others, and you're stuck. And again, like it's up to you to experiment with it. But if you will implement some environment, you will quickly see that algorithms usually cannot hold these numbers of the robot and the complexity of the algorithm.
But I don't understand the number of reasons. I mean, imagine that there should and that's the obsession. Then if I have 10,000, right? What does this look like here? But they are far away.
I mean, like it's a good question. I mean, the thing that the Windows approach can probably work because you still will take into account only small window. How good it will behave, I cannot answer on this question. Like we didn't experiment for so many robots.
Yeah, I wanted to comment on this one actually. So you really don't need always collaborative. And this how it actually worked for us. So that the things that always work is like kind of road rules, and every robot decides for itself, right? So this like a baseline you can always implement, but the problem is, if you have enough space. So there are some configurations. I don't know if you know Ocado, or there are like some systems where they're like fully automated warehouse where there is a lot of robots in a very limited space. So there you can just not, like you don't have this option. So you have to have collaborative global planning But yeah, sometimes you're right. You don't really need cooperation that much. But the more limited space you have, the more you need it. And sometimes this is your only way.
I think we'll probably start here. And yeah, thank you for the questions.
Minutes.